All right, hey everyone, welcome to our next lesson. Today we will be talking about inverses and one-to-one functions. Your aim is how do we find the inverse of a one-to-one function? Homework's going to be number 12 in the OpenStax textbook, page 110, numbers 9 through 13, 19, 21, and 23. Okay. Here are your objectives for today. So first we're going to define a one-to-one function and give an example of an equation that is one-to-one. We're going to perform the horizontal line test to verify if a function is one-to-one. Third, we're going to find the inverse of a given function algebraically and use the correct notation. And fourth, we're going to use compositions. So that was the previous lesson to verify that two functions are inverses. Okay. And with that said, let me get to the do now, which is going to make use of this diagram here. All right, here is the do now. Okay, so for the following two functions, do the following. Part A, list the ordered pairs for each function. Part B, explain what is different about function G. Okay, so as you can see in part F, function F, you have 1, 2, 3, 4 in the domain, and then 10, 7, 4, 2 in the range. 4 gets mapped to 10, 3 gets mapped to 7, 2 to 4, 1 to 2. For function G, 4 to 10, 3 to 4, 2 to 4, and 1 to 2. And then as you can see, function G is different because 3 and 2 both get mapped to 4. And there's also no 7 here because of that, right? So there's one less element in the range. But yeah, let me get to the solution for that. Okay, so here the answer is F has 4, 10, as we just saw, right? 3, 7, 2, 4, 1, 2. So that's how you would write the ordered pairs. For function G, it's 4, 10, 3, 4, 2, 4, right? Because both 3 and 2 get mapped to 4. And lastly, 1, 2. Okay, so that's your answer for part A. Part B, function G maps two different x values, namely 2 and 3, into the same y value. I.e., that's the Latin for that is id est, I-D-E-S-T. So the literal translation of that would be that is, okay, just quick lesson for you in Latin there. That is G of 2 equals G of 3, right? So both G of 2 and G of 3 equal 4, right? Because they both can map to 4. Okay, so as a follow-up to that, there's this diagram from the old textbook, right? F is one-to-one function, right? Because each x value gets mapped to its own y value. And then G is not one-to-one, right? So both 2 and 3 get mapped to 4. So this would not be one-to-one. Okay, you remember this concept from Algebra 2. And also I did show this definition in, I believe, was the range video, because that topic was relatively short. So I just wanted to throw that in here, or in that video, I mean. But yeah, let me go through it again today. But yeah, if you need a copy of this do now solution, please pause the video here. Otherwise, I'll show you what we're going to do for the rest of the video. Okay. All right. So just as an overview, we're going to go through the definition of one-to-one functions again. We're going to talk about the horizontal line test. We're going to go through two examples, so x cubed and x squared, see whether they're one-to-one or not. And then, so that's the first half of the video. And then the second half of the video is going to be about inverses. Okay. And as you can see, or as you might know, inverses and one-to-one functions are closely related. Okay. So for inverse functions, we'll go through the definition, discussion question, the inverse function property, and then how to actually find the inverse of a one-to-one function, and then the example, and that'll be followed by some questions on the classwork. Okay. All right. So with that being said, let me get to the slide. All right, so here's the definition of a one-to-one function. So a function with domain A is called a one-to-one function if no two elements of A have the same image. That is, f of x1 is not equal to f of x2 whenever x1 is not equal to x2. Okay, there's a bell. All right, pardon the interruption. Okay, an equivalent way of writing the condition for a one-to-one function is if f of x1 equals f of x2, then x1 equals x2. Okay, so please pause this here, and then I'll talk about it. Okay. All right, but let me start off by reminding you of the analogy that I used in the range video where I introduced this definition. So if you remember, the analogy was Bronstein students to OSIS numbers, right? Because each Bronstein student has their own and unique OSIS number, right? So if you have two different Bronstein students, they'll have two different OSIS numbers, okay? So to relate that to this definition, f of x1 is not equal to f of x2 whenever x1 is not equal to x2. Okay, so whenever you have two different students, that will mean that they have two different OSIS numbers. Okay, so x1 is not equal to x2. That means you have two different Bronstein students. Therefore, f of x1 is not equal to f of x2, right? The OSIS number of person one will not be the same as the OSIS number of person number two. Okay, all right, so to relate that to this definition, or the equivalent way of writing it, if f of x1 equals f of x2, so if you have two of the same OSIS numbers, then x1, right, person one or Bronstein student number one is equal to Bronstein student number two. In other words, if you have two of the same OSIS numbers, this must mean that the two people in question are actually the same person. Okay, that's how you would see it. Okay. All right, well, if you need to still copy this down, please pause the video here, but otherwise I'll move on to the discussion. Okay. All right, so here, explain the significance of the horizontal line intersecting the graph at more than one point. Okay, so this is alluding to the horizontal line test. So as you can see, right, you have x1 equals, x1 and x2, right? They're not the same. And you have the corresponding y values, f of x1, f of x2. Okay, so as you can see, this, this will not be one-to-one, right? Because if you have, to use the analogy, right, two different Bronstein students, they both get mapped to the same y value, which means that they have the same OSIS number, which is a problem, right? Because we wouldn't be able to identify that student, okay? So therefore, if the horizontal line passes through more than once, that would mean that the function is not one-to-one. Okay, I'll say that again. So if a horizontal line passes through a function more than once for the same y value, that would mean that the function is not one-to-one. Okay, let me get to the answer for that up here. Okay, so here it is. If a horizontal line intersects the graph at more than one point, we see that f of x1 equals f of x2, right? They're the same y value, right? Let's say it's like 5, you know, even though x1 is not equal to x2, right? So the function f is not one-to-one. Therefore, we have the following geometric test. And for that, let me show you the definition. All right, so horizontal line test, and then as you can see, we'll get into these examples. A function is one-to-one if and only if no horizontal line intersects its graph more than once. Okay, a function is one-to-one if and only if no horizontal line intersects its graph more than once. Okay, not to be confused with the vertical line test, which tests whether the relation is a function. Horizontal line test is for testing whether it's one-to-one. Okay. All right, if you need to copy this here, please pause the video. Otherwise, we'll jump into these next two examples. Okay, so first we have x cubed, right? So here's the solution provided by the old textbook meaning the one we would normally use in class. So if x1 is not equal to x2, right, then x1 cubed is not equal to x2 cubed. Another way of saying that is two different numbers cannot have the same cube. Therefore, f of x equals x cubed. Sorry, f of x equals x cubed is one-to-one. Okay, so x cubed is one-to-one. Okay, if you didn't like that explanation, you can always use the horizontal line test. Okay, so from figure 3, which is this figure here, we see that no horizontal line intersects the graph more than once. Okay, so whenever you draw a horizontal line, then it just passes through once. Pardon the second interruption. Therefore, by the horizontal line test, f is one-to-one. Okay, so yeah, horizontal line doesn't pass through more than once. It's one-to-one. All right, if you need to copy this, please pause the video here. Otherwise, I'll be moving on to the next example. All right, x squared. Okay, so x squared, is this one-to-one? So first type of solution is algebraic, right? This function is not one-to-one because, for instance, g of 1 equals 1 and g of -1 equals 1, right? And so we can see that 1 and -1 have the same image. Okay, image, that's just a fancy word for output. Okay, and if you didn't like that explanation, you can always use the horizontal line test. So from figure 4, which is this figure here, we see that there are horizontal lines that intersect the graph more than once. Okay, so like this line, right? Therefore, by the horizontal line test, g is not one-to-one. Okay, so x squared is not one-to-one. Okay, if you need to copy that, please pause the video here. Otherwise, I'll go on to this follow-up question. So although the function in example 2, so the last example, is not one-to-one, how can we restrict the domain so that it is? Okay, and the reason I'm asking this is because there are some times where we want to restrict the domain so that it is one-to-one, so that, and this is a segue into our next topic, which is the inverse of a function, which you see here. So if it is one-to-one, then we can make an inverse, right? So only one-to-one functions have inverses, which we'll discuss in just a sec. But yeah, that's why we would want to restrict the domain sometimes, okay? But yeah, as you see here, the answer is if we define h of x equals x squared with domain x is greater than or equal to 0, the function is one-to-one. Okay, so anything that's positive or 0, so if you just have the right-hand side of the graph, then the, I guess, parabola, or half the parabola, this function would be one-to-one, and it would have an inverse. Okay, but yeah, that's a segue into our next half of the lesson, which is the inverse of a function. Okay, for that, let me get to the definition. Okay, all right. Here's the definition of an inverse. All right, so let f be a one-to-one function with domain A and range B. Okay, so that's what we're going to call the domain, A and range B. Then its inverse function, f inverse, has domain B and range A. Note that they're switched, right? And is defined by f inverse of y equals x, and f of x equals y. That's the corresponding function. Okay, so in other words, this is just saying that the inverse function undoes what the function did. Okay, so if you have y as the output of the original function, and if you plug that value into the inverse, then you get back the corresponding x value. Okay, and then for any y and b. Okay, if you need to pause that here to copy it down, please do so now. Otherwise, I'll be going to the discussion. Yeah, but yeah, you can see the discussion here, but let me just jump to back to the lesson so that you can see the answer also. Okay, so let's explain why a function has to be one-to-one in order for it to have an inverse. All right, here we are. Okay, so by definition, the inverse function f inverse undoes what f does. If we start with x, apply f, and then apply f inverse, we arrive back at x where we started. But if there are two x values assigned to the same y value, then we wouldn't know where to end up. Okay, so for this example, let me use the example of a parabola. Okay, so as we know, this is not one-to-one. All right, so sorry, pretend that's a horizontal line. But yeah, let's say you have this value of -1 and 1. Right, so as we know, -1 and 1 both get mapped to the y value of 1. Right, so as we know, the inverse function undoes the original function, right? So if you give the inverse function the y value of 1, or if you input this y value into the inverse, it has to give back the x value that brought you there. Okay, so meaning it would have to tell you -1 and 1, right? Two different answers, which is not okay because that will make it not a function. Okay, if you remember the grocery store analogy, that would be like an apple costing two different things, right? Two different prices at the same time. So that will make the inverse function not a function. Okay, but we need the inverse function to be a function. Okay, I guess if you didn't need to be a function, that's okay. But yeah, so that's why it has to be one-to-one in order for it to have an inverse. Because if there are two x values assigned to the same y value, as you see in this example, then we don't know where to end up, right? Because if they both get mapped to 1, and we put if we evaluate f inverse at 1, then it has to provide two answers, which is not okay, right? At least, you know, if we're considering f inverse to be a function, which we do want. Okay. All right. For the rest of the lesson, it's just going to be some notes, and then we'll get into the classwork. Erase that. All right, so I'm going to show you the inverse function property, and then finding the inverse of a one-to-one function, and then the classwork. All right, here's the inverse function property right here. So let f be a one-to-one function with domain A and range B. The inverse function f inverse satisfies the following cancellation properties. So this is going to make use of the composition of functions, right? F inverse of f of x equals x for every x in A, and f of f inverse of x equals x. So if, in other words, if you compose the inverse with its original function, then you just get back the variable x. Okay, so that's true for any one-to-one function and its inverse. Okay. If you need to copy that, please pause the video here. Otherwise, I'll be moving on to the procedure for finding the inverse. Okay, so here's the procedure. So in the last, few minutes, we talked about the properties of inverse functions. But here's how we actually find it, right? So first, you're going to write y equals f of x. So just change f of x to y, and then solve this equation for x in terms of y if possible. And then interchange x and y. The resulting equation is y equals inverse. That's going to be your inverse function. Okay. You might remember this from algebra 2. So actually, you can interchange x and y first and then solve. Doesn't matter. You're going to end up with the same answer. Okay. But yeah, I'm going to jump to these examples. And actually, I think I deleted this first example. But yeah, let me get back to the lesson plan for that. But yeah, if you need to copy this procedure down, please pause the video here. Okay, so for the example, okay, so find the inverse of the function f of x equals x to the fifth minus 3 divided by 2. So you first write this function. So first write f of x equals y. So replace f of x with y, and then solve for x. So remember, you can switch x and y first and then solve, but the textbook, they solve first and then switch. Okay. So solving for x, they multiply both sides by 2. You get 2y equals x to the fifth minus 3. And then you're going to they add 3 to both sides. So you get 2y plus 3, which they switch the sign, right? So 2y plus 3, and then that equals x to the fifth. And then you take the fifth root. Right? So x equals 2y plus 3 to the 1/5 power. Then they interchange x and y to get y equals 2x plus 3 to the 1/5. Therefore, the inverse function is 2x plus 3 to the 1/5, okay? Or the fifth root of 2x plus 3, okay? If you need this solution, please pause the video here. Okay, but yeah, very briefly before we get into the classwork. So to double check your results, we use the following. So we're gonna use the inverse function property. But yeah, that was the inverse function property that I mentioned earlier. So you can just compose these two functions. I'm not going to go into detail into this. I didn't want to emphasize this, but yeah, if you see, you'll compose these two functions and then you just get back x. And for the same thing for the reverse order, right? F of f inverse of x, you also get back x, right? So that's how you would show that they are in fact inverses of each other, right? The function and its inverse, they are in fact inverses. Okay. All right, with that being said, let me get to the classwork. Okay. All right, here's the classwork. Just a few quick questions. So numbers 1 to 4, we're going to determine whether it's 1 to 1, and then for 5 and 6, we're going to find the inverse. Okay. So these I'm going to solve algebraically. Of course, you can always solve these questions using the horizontal line test, but I'm going to provide the solutions here as algebraic. Okay. All right, number 1 is x to the 4th plus 5. As we know, that's going to look like a parabola, right? So x to the 4th is going to look parabolic, but it's not 1 to 1 because you have two different x values equaling the same y value. So if you plug in -1 and 1, you'll see that they both equal 6. Okay, so this first answer is not 1 to 1. Okay, and actually, let me type that to make it clearer. Yeah, it's not 1 to 1. All right, question 2. f of x equals x to the fourth plus 5. So note that here we limit the domain to 0 to 2. Okay. And in this case, it is going to be 1 to 1 now, because if x1 is not equal to x2, then x1 to the fourth is not equal to x2 to the fourth, because two different positive numbers can't have the same fourth power, right? And you can test that out, right? Like 1 to the fourth power is not going to be the same as 2 to the fourth power, right? So in other words, x1 to the fourth power plus 5 is not equal to x2 to the fourth power plus 5, okay? So if we limit the domain here, then it is 1 to 1, okay? All right, next we have 1 over x squared, and this is not 1 to 1, because as you can see, if you plug in two different x values, -1 and 1, they both equal the same y value of 1. Okay, so this is not 1 to 1. All right, followed by 1 over x, and this is 1 to 1. Okay, because if you have two different x values, then 1 over x1 is not equal to 1 over x2. Okay, and yeah, you can test that out, right? 1 over -1 is not going to be the same as 1 over +1. Okay, yeah, so this is 1 to 1. And remember, yeah, as always, you can use the horizontal line test for these questions. Okay, but yeah, if you need the solutions to for 1 through 4, please pause the video here. Otherwise, I'll move on to 5 and 6. Okay, so 5 and 6, we have to find the inverse of the following. So 2x plus 1. So these are going to be pretty simple. Okay, so first I wrote f of x as y. So y equals 2x plus 1. And then I'm actually going to switch the variables first. Oh, sorry, I didn't switch. I just switched the sides. So I just subtract 1 from both sides. You get 1 minus 1 equals 2x. So y minus 1 equals 2x here. I just switched the equal sign, right? And then I'm going to divide both sides by 2 to get x equals 1/2 times y minus 1. Okay. And then therefore the inverse, all right, this is the inverse function. We just have to switch the x and y variables. So the inverse function will be 1/2 times x minus 1. That's your inverse function. And again, you can always switch x and y first if you find that easier, okay? But yeah, that's your answer for number 5. All right, for number 6, f of x equals x over 2. So I'll write that as y equals x over 2. And then I'm going to multiply both sides by 2 to get x equals 2y. Okay, and then you can switch the variables. So y equals 2x, and you can change y into f inverse. So f inverse of x equals 2x, and that'll be your answer for question number 6. Okay, but yeah, with that being said, please remember to submit your homework. And oh, well, if you need to copy the solution, please pause the video here. But yeah, if you need to, so here's the homework. Please remember to submit it by tomorrow night. And other than that, that's all I have to say for today. I'll see you all in the next lesson. Have a great rest of the day.